So, we will continue with the discussion on Franck Condon principle. So, if you would remember what we did last class was that we had derived this relation for a transition moment, right, and you can see that this transition moment had this expression, final expression. So, there were, it could be grouped into two. The first one, which has the electronic dipole moment operator, where E stands for electronic, right. So, it has in the Dirac notation the psi electronic prime, okay, which is excited state electronic, then the mu E, the electronic dipole moment operator, then psi electronic double prime, which is your ground electronic state, right. So, this, if you would do this integral, this would be based on electronic transition only, okay. There is no vibration involved now, only pure electronic, right. But as we have seen, that your electronic motion is also to a certain extent governed by the nuclear coordinates, right, because you cannot separate it out. In time scale you can separate it out, but then the electronic coordinates will always, or the electronic motion will always have a parametric dependence on the nuclear coordinates. Hence, you will be having this vibration overlap coming into. So, the next one was your vibration overlap or the Franck Condon overlap. So, this tells you which two vibrational states, one from the ground state and one from the excited state, are overlapping most, and that is where the most intense vibration or the most intense transition would be, okay, because that is where you have the largest overlap in terms of the wave functions, right. And we also said this, that if you would take the square of this, you would get the Franck Condon factor, and the Franck Condon factor is the one which finally determines the intensity of the transition you are happening, or you are looking at, or transition that is happening. That means, the intensity is proportional to the Franck Condon factor, which is the overlap squared. Okay. So, coming back to the slides now. So, this is what we looked at last night. We talked about this Franck Condon envelope, right, and what we said was that you do not have only one transition. Instead, what you have is you have a series of transitions. The series of transitions results because of the fact that it is not that the electron density is only there at one position, you have an electron density throughout, that it's it's kind of a delocalized thing, and hence because of this. So, because of this you can be having transitions from here, you can be having transitions from here. So, that means the transition can occur throughout the band wherever you have the wave function out there. Okay. This would give rise to your Franck Condon overlap. So, that is how you see. So, in the first case what you would see is that in this case the 0 to 1 is the transition having the maximum intensity. In the next case the 0 to 4 is the transition having the maximum intensity. The difference between these two being, in the latter case, that means in the second case you have a much larger difference in what, the internuclear distance in the ground state and the excited state. Now, that is typically how it comes about. Okay. So, moving on, again we are looking at the Franck Condon envelope. So, if you take a look at this, I am talking about this at length because if you would take up an absorption spectrum, so mostly of organic molecules, you would always see these structures coming in. Okay. And what are these structures due to? These structures are essentially your vibronic transitions. That means, your transitions where vibration is coupled to your electronic motion or electronic transition. You would typically see those. Now, obviously, to what extent you see those will also depend upon the conditions, that means the solvent conditions and everything, right. But again, looking at this Franck Condon envelope, so between the ground state and the excited state, where the ground state is E0, the excited state is E1. There, here you see that the way this one is drawn, that means the way the higher potential energy has shifted, what has happened is the which one would be the most intense transition for the absorption in this case? Which one do you think would be the most intense one? 0 to 2, right. So, the most intense one would be 0 to 2, right. Now, this was the absorption, right. So, this is your absorption, A, absorption, right. Now, what happens is, if it is going to go up, it is also going to come down, right. It can come down either by emitting light, that means emitting photons, or by not emitting photons. So, if it emits photons, it would be called radiative transition. If it does not emit photons, it would be called radiationless, that means it does not radiate any photons, it does not give out any light. Okay. So, it does not matter whichever way it comes down, if you look at it, the coming down would be very similar to the way it went up. That means, if it went up vertically, the coming down will also be vertical, because the coming down is again a movement of electrons, right. So, again the Franck Condon transition is not only vertical in one direction, it is also vertical in the other direction, because what are you playing with? You are essentially dealing with the movement of electrons, right. So, essentially now what you can see out here is, based on this, if this green one is, well, say it is fluorescence, I will come back to fluorescence later. If this green one is fluorescence, so even for fluorescence, now tell me which one would be the most intense transition. See here it is occurring from V prime is equal to 0 in the excited state and coming down to a high vibration level in the ground state. Now, which one is it? It is again 0 to 2, is not it? Okay. So, that means while going up you had 0 to 2 as the most intense, while coming down you again have 0 to 2 as the most intense, and this you do not have to think about, it is just evident from the way the picture is being shown or the picture is drawn. Okay, that is where you have the maximum overlap. Okay. So, then if you would draw this Franck Condon overlap, this is how it would look. So, let me tell you, the blue one is the energy, the green one is fluorescence, right. So, energy, absorption is always higher in energy than fluorescence, remember. There is something known as Stokes shift, we will come to that later, but anyway. So, if this is energy, so on the higher energy side, that means to the right side you have the absorption bands, to the left side you have the fluorescence bands, right. So, what you can see out here is, in the absorption as we discussed, the 0 to 2 is the most intense one. Similarly, for fluorescence the 0 to 2 again is the most intense one, but we have to have an overlap, that means we have to have a progression, because the other transitions are also available, and that is how the other intensities go. Okay. So, these are now, so you are just plotting the respective transitions. Now, remember one thing, this will not be able to cover in details, but try to appreciate the fact that if you would be having this in a solvent, I am not talking about a gas phase, I am talking about a solvent, say water, okay, or say any other solvent. What will happen is your solvent molecules will always collide, right. So, because of these collisions and because of these interactions, what it will do is, it will not keep your spectrum as narrow, it will actually broaden it, because you have so many interactions with the surrounding solvent molecules. Okay, this is called a type of broadening coming in. Okay. So, because of this broadening, what you will see is, when you finally see the spectrum, you would not be able to see these individually like this. Okay, you would not be able to see this individually, no. Instead, what you would see is, you would see these possibly, depending upon how much of interaction, how much of broadening you have, they will be merging with each other. Okay. And how do you visualize that? It is very simple. You look at this line, you look at this green line and this blue line out here. What is this solid line? Can you tell me what is this solid line on the right side, that means along with the absorption? First of all, see the way the solid line goes is, see the solid line. So, if you are talking about this solid line, this is the one which is the absorption one, right, the absorption solid line. If this is the one you are going with, where does it max? It max at 0 to 2, right. Then the next maximum is at what, about 0 to 5 or whatever. Okay. So, essentially guys, this is the absorption spectrum. So, if you were to take an absorption spectrum of this sample in any given solvent, say, this is how the absorption spectrum would look like, and what you can see in the absorption spectrum is that you do not any longer see those vibrational structures. The reason being that they have merged together because of too much of broadening, right, too much of interactions, that is why. But it is not like this that you will never see those, it actually also depends upon the rigidity of your molecule, how rigid your molecule is, how not flexible your molecule is. Okay. But anyway, so if this is the absorption spectrum, so this is the absorption spectrum essentially. So, this is your absorption spectrum. Similarly, if you go to the fluorescence, you also look at the fluorescence spectrum. Okay. Now, just to make a passing comment, two things. One is the 0 to 0 transition which you see here, the 0 to 0 transition which you see here. Okay. This is a transition which should be, equi-energetic for both fluorescence and absorption, right. You are going from 0 to 0, that means in absorption you are going from 0 to 0, in terms of fluorescence you are also going down from 0 to 0. So, they coincide, they fall at the same place. Okay. Number 2 is, you look at the fluorescence. In the case of the fluorescence spectrum and the absorption spectrum, if you forget everything else, if I place a mirror like this in the middle, if I place a mirror, wouldn't you say that your fluorescence spectrum is actually a mirror image of your absorption spectrum, right? You place a mirror and you will get the mirror image, right. So, this is called mirror image symmetry or mirror image rule. Okay. Now, this I will discuss this later, but just to let you know, because we have this picture in front of us. This arises because whatever vibration levels are involved in the absorption, the same vibration levels are involved in fluorescence. That is essentially why it comes. Okay. So, in most cases, especially in cases where you would see the molecules are very rigid, there are not too much of change in the equilibrium bond length, this mirror image symmetry is typically maintained. Okay. Now, this is another example. See, the another example is again for the same Franck Condon overlap. So, you look at the one which is on the left and the one which is on the right. On the left, you see there is almost no change in nuclear configuration, that means R equilibrium is the same, and hence if you come down, you see it is a 0 to 0 transition is the one which is the maximum. Okay. Similarly, if you go to the right where R equilibrium has changed, then what happens is here 0 to 0 is no longer the maximum, but 0 to 2 has become the maximum. Okay. Now, this is what you would ask. What you would ask is, okay, I have this the solid lines. Now, what are the broken lines? Can someone tell me what the broken lines are? Obviously, the broken lines are the one which correspond to the peak, right. So, 0 0 wherever you have the peak, you have the broken line, then 0 1 0 2. Okay. What are these? Well, this is a wavelength. It is on the wavelength scale, that is understood, right. So, remember 0 to 0 has the lowest energy. So, it will be having the highest wavelength. Any other transition 0 to 1, 0 to 2, 0 to 3 would be having a high energy, and hence would move to the lower wavelength slide. Okay. In the next slide, what you will see is instead of lambda, we will be plotting it in terms of centimeter inverse, and then it would just swap, right. But anyway, coming back to the broken lines, you know where the broken lines are coming from. If you would take this molecule, okay, the solid lines are coming from this molecule being in condensed phase, say in a certain solvent, depending upon what it is, an organic solvent or water. Now, what happens if I take the molecule to the gas phase? What will happen? If I take the molecule to the gas phase, what are you getting rid of? You are getting rid of the solvent molecules, right. But by getting rid of the solvent molecules, what are you getting rid of? You are getting rid of interactions. That means you are getting rid of a lot of broadening. So, if you take this molecule and look at the vibration transitions or the vibronic transitions in the gas phase, the broken lines are the ones which are the spectroscopic transitions you would be seeing in the gas phase for the same molecule. Okay. So, the broken lines, these broken lines are those collected in the gas phase for the same molecule. So, this essentially tells you when you go from a gas phase where you have no solvent molecules, none of these broadening, when you come to the solvent state, you see how broad your spectrum becomes. I will give a simple example. This you guys know, okay. It is not from fluorescence, it is from vibration transition, or it is not from electronic, it is a vibration transition. Now, think about the OH stretching band of water in the IR. Where does it, what is the range of OH stretching band? 3600 to 34, 3300. Why is it so broad? Have you ever thought about it?
Hydrogen bonding exchange.
Right, hydrogen bonding interaction. So, you have different types of hydrogen bondings out there, and hence that gives rise to many different vibration transitions, and then it increases the width of your spectrum. Okay. The same thing is happening here. There hydrogen bonding is happening with your solvent water or whatever solvent you have. Here in the gas phase you do not have that, and hence it becomes so narrow. Okay. But it does not mean that it is a single line, right. It still has a certain width, please remember that. Okay. So, again you go from left to right, see what happens. The left one there is no change. So, it is a 0 to 0 transition. So, this is the 0 to 0, 0 transition is the maximum. Now, see what happened is I have changed the scale. Initially the scale was lambda, now the scale is what? Centimeter inverse. So, because it is proportional to energy, the 0 to 0 one is the one which should be having the least energy, that means the least centimeter inverse. Okay. Because delta is equal to what? HC nu bar, right, and delta is proportional to your nu bar. Now, when you go to the next one, now you can see, so here what, it is 0 to I guess 2, right. Then in this case it is also 0 to 2. Interesting case is the last one. Okay, the first two you kind of have seen, you kind of would realize what is going on. Tell me what is happening in the last one. Tell me what is the difference between the first tree and the last one. Do not look at the spectrum down, Just look at the two potential energy curves and tell me what is the difference. See where this arrow ends up. Where does this arrow end up? This arrow ends up here in the last one. See, if I take this, if I draw a vibration level out here, the vibration level will go like this. Okay. In all the other cases, the arrows were not that high up, right? The arrows were already there, or the arrows were always there where you had these blue lines, streaks going through. So, what is the difference between the red vibration level I drew and the blue ones in the same potential energy curve? That means, what is the difference between these ones and this one? What do you think is the difference? Huh? Well, I would not be saying no vibration level, but go ahead, just well, closely spaced, still a little more dissociation. Thank you. See, when you have these vibration levels, these are bound within your potential energy, right? See, what does quantum mechanics arise? Where do these quantum numbers arise from? Typically boundary conditions, nothing else. The moment you impose boundary conditions, you have quantization, right? That is what quantization is all about. Now, when you go to this place, is it any longer bound on the other side? Because you see your potential energy is already ended out here. That means it looks like this and your vibration level goes like this. That means this one is already beyond your bound state, it is no longer a bound state. If it is no longer a bound state, what does it mean? If it is no longer a bound state, what does it mean? That means the molecule has the probability to dissociate out there because it is not bound anymore. So, the molecule will go ahead and dissociate. The moment the molecule dissociate, what will happen is, now think about this, if you are going to a non-bound state, what happens to the quantization? Do you have quantization anymore? No, right? Because there is no bounds anymore, no quantization. So, the spectrum becomes what? Continuous. Okay, now come to the spectrum down, and do you understand where the continuum comes from? Okay, so, the continuum comes from the fact, see, that is the one where it is most intense. That means, if you are doing a vibration transition to that place, the molecule would be having the probability of dissociating. So, this is a transition which ends up dissociating your molecule, right. See, the fact is very simple. The fact is that if you think about this about it like this, you do a transition, right, and you have a change in bond order, say. So, you have such a huge change in bond order, that means there is such a huge change in your equilibrium, that means the nuclei have moved so far apart that they almost feel no attractions, right, and hence it is very easy for them to come apart. So, hence they dissociate. So, that is typically what happens when you do a photo-dissociation. That means you go to the excited state surface where your things are not bound, you have a dissociative potential energy surface and it dissociates. Okay. Here I am not showing a dissociative potential energy surface. What I am telling you is that on the same excited potential energy surface, the vibration level excited at is typically the one which is not bound by your potential energy, and hence it is a continuum. So, that is why this continuum results. To tell this to you a little more clearly, you go on to this part. Okay. So, this is exactly what the thing you are seeing out here. So, you see the green line goes here, right. You can see already, remember in an anharmonic oscillator, as you go up, what happens to the spacings? They decrease anyway, right. When you come here, your boundary ends. So, any vibration level on top of that would actually be not bound, and hence if you are exciting to that level, what will happen is it will easily dissociate. So, that is what it is referred to as a dissociation limit. So, you can understand, if you are doing a transition out here, up till here it is bound, any transition beyond that will induce dissociation or photo dissociation in the molecule. Okay. Now, try to connect this to what we have done just in a simple way. Remember, we talked about this optical triggering by flash photolysis. You remember that, right? That means we were breaking the bond between the CO, that means this carbon and the iron. So, this is essentially what was happening. So, that means you would hit it with light, a certain wavelength which you would absorb, right, and that light would be such that would absorb, it would go to a state where that bond would break. That means you are into a dissociation region and the bond snaps. Okay. So, this is another way of looking at it. Okay. So, this was about your Franck Condon overlap, whether you are looking at an absorption spectrum, that is what we have mostly talked about, whether you are looking at a fluorescence spectrum, and as I said, in many cases fluorescence spectrum is a mirror image of absorption spectrum. Okay. This is how the transitions happen. If you are looking at one side like this, the other side typically follows. So, you can just parallelly draw those transitions and see which one is the maximum. Okay. Now, let us talk about this optical phenomenon known as absorption, okay, this technique. So, the basic equation in absorption is what? The Lambert-Beer's law, right, that is what we use. Good. So, let us look at that Lambert-Beer's law real quick. So, what I do is I will actually derive Lambert-Beer's law for you, okay, real quick. So, what I do is I have a section of my solvent, that means my sample which has the absorbing molecule in a solvent, okay. And what I do is I take a section like this and I say that the incident light on this is I 0, having the intensity I 0, and the light that is coming out or transmitted is say I. Okay. Now, what I do is in this I take a very small section, I say this is dx, very small section d of x, and what I also give you is the length of this is L, okay. So, total length is L, the total length of the absorbing medium, right. So, what is I 0? I 0 is the intensity of the incident light, and what is I? I is the intensity of the transmitted light. I am not writing those things down, okay, this you guys know. Now, let us assume that we have n absorbing molecules per centimeter cube, that means per unit volume, where the volume is in centimeter cube. Okay. What I also say is that let sigma, this is called sigma, be the absorption cross sectional area. Okay. Let this be the absorption cross sectional area. Now, tell me, when you are going to have absorption, right. So, suppose you are hitting it with I 0, then the I comes out. So, that means if it is going to absorb, there would be a difference between I 0 and I, and that is going to tell you how much it is absorbed, right. So, suppose if I am looking at this fragment, if I am looking at this infinitesimal element dx, then the corresponding intensity change say is di. Okay. So, what would di by dx be proportional to? That means the amount of change in intensity I have over that unit interval, or over that interval dx, should be proportional to what? First tell me. There will be three factors I am telling you. Let me give you one hint is the number of molecules, right, obviously, because the more molecules we have, more we will be absorbing. What is the next one? Intensity, very good, the intensity with which you had hit. What is the other one? It is written out there. Cross section area. It is cross section area, right, because if you have a molecule which is like this and if you have a molecule which is bigger, then obviously this one would interact more and would be absorbing much more. So, then based on this what you can write is di over d of x is equal to minus I sigma n, and let this be 1. Simple, right, that is what I just said. It is a negative sign because you know that it is being absorbed, the di would decrease, means the intensity is going to decrease. Okay. So, now what I do is I impose boundary conditions, that means I say that at x equal to 0, that means at x equal to 0, I equal to I 0. Now, what does x is equal to 0 mean? X is equal to 0 means this. See, I had taken dx, so x is equal to 0 means would be this one, x equal to 0. So, that means x is equal to 0 where it has not yet entered the sample, I have the intensity I0, that means nothing has absorbed. Good. Now, what I also say is at x equal to L, what is L? L is the other side because L was the total length. So, then this I would be I, right, this much is coming out. So, then what I can write is, if I would integrate 1 based on the aforesaid boundary conditions, based on the aforesaid boundary conditions, this is what I am going to have. What I am going to have is, I am going to have d I over I is equal to minus I sigma d of x. Okay. Integrate. So, you are going from x is equal to 0 to x is equal to L, you are going from I 0 to I. Okay. So, there I can write this, right, sorry, this should be n, right, thank you. So, here n would be coming in. So, ln I 0 by I should be equal to what from here? Now, see, I have changed the order a little bit. So, this should be equal to what? I should be having sigma, I should be having n, and then I should be having L. So, this is equation 2. See, this is a form of your Lambert-Beer's equation. Okay. So, this is a form of your Lambert-Beer's law, right. The only thing is, this is not what you use frequently. What you use frequently rather is, what you use frequently is, the frequently the Lambert-Beer law is expressed as log of I 0 by I is equal to epsilon C times L, right, and this is equal to your optical density, and this is equation 3, and this is equation 3. Okay. So, the bottom one is the one you use frequently. Now, obviously, these two are coming from the same principle. So, these two would be comparable, these two would definitely be comparable, right. So, you compare these. So, what you do is, you compare equations 2 and 3, and this is what you end up with. What you end up with is sigma is equal to 2.303 epsilon C over n. This is 4. That means, your molecular cross section area, or absorption cross section area rather, not molecular absorption cross section area, is equal to 2.303 times the epsilon C times C over n. 2.303 comes from that conversion factor ln to log, log to ln, like that. Epsilon is referred to as the molar decadic extinction coefficient. Okay. Please remember one thing, this epsilon is intrinsic to that respective molecule, and this epsilon also depends upon lambda. It is not the same for all lambdas, okay, you will see that soon. So, I can say epsilon is essentially a function of lambda, please keep that in mind, it is always a function of lambda. Okay. Now, what I do is, from equation 4 what I can do is, I want to replace n. What I want to bring in, what is n? N is the number of molecules per centimeter cube, that is what I said. Now, suppose I want to find the number of molecules, how would I do that? So, for example, if I want to do n, what was concentration C? C is moles over liter, okay. C is always moles over liter, okay. If I am going to get the number of molecules, what would I do? I would multiply it by the Avogadro's number, Na, okay. So, I would be having Na times C, but this is the number of molecules per what? Per liter. but what was my volume unit in this case? Centimeter cube. So, what I have is Na times C over 10 to the power 3, and please remember C is given in moles per liter. Okay. So, epsilon comes in mole inverse centimeter inverse. So, this is m and epsilon is mole inverse centimeter inverse. You can understand one thing. One thing is this log of I 0 by I, should it be having any units? It should be unitless, right? Where it is a ratio of two similar things, it should be unitless, no unit out there. Okay. So, that is how you get this. What I did not mention was, because your volume is in centimeter cube, your L has to be in centimeter, right. So, that means I can also write your L is in centimeter. Okay. So, finally, based on this, if you use this value of n in 4, that means use n in 4, what you get is sigma will be equal to 2303 okay, over N A times epsilon. So, what you are looking at is a relation between something fundamental you always know, which is the extinction coefficient or the absorption coefficient from Beer's law, to something which you probably have not realized before, which is the cross section area of absorption of that molecule. Okay. That is something which is very fundamental, and to tell you the truth, if you are doing spectroscopy, hardcore spectroscopists would not talk in terms of extinction coefficient, they would rather talk in terms of cross section area, because you see when you did the derivation you never talked about extinction coefficient. What did you talk about? You talked about the area of this molecule interacting with the incident radiation. Okay. So, this is something much more fundamental in terms of a spectroscopist's point of view. Okay. Good. So, if you do the math, then you will see this sigma would come out to be about 3.82 times 10 to the minus 21 times epsilon, let this be 5. So, there is a relation, and I will give you an example by taking a molecule. Okay. So, let me repeat again what a cross section area is. When light is coming in, that means photons are coming in, photons have to interact with the molecule, right. If the photon is going to interact with the molecule has to present a certain cross section area for interaction. This is the cross section area you are talking about. Wherever the cross section area of interaction is high, your absorption would be high. Wherever the cross section area of interaction is low, your absorption would be low, and that would lead to your corresponding extinction coefficient. So, that is why it all starts from the cross section area. Okay. Now, let us see whether we can give an example and try to realize where what we are talking about. Say, think about this molecule anthracene. This molecule anthracene. For the molecule anthracene, what you are told is that the epsilon value at 253, that means 253 nanometers. Okay. So, that means the extinction coefficient at 253 nanometers is given by this number, this is 1.6 times 10 to the power 5. Okay. Similarly, it also absorbs at another wavelength where the extinction coefficient is given by, this is 375, this is equal to 6000 mole inverse centimeter inverse. Now, see the difference. In one case the extinction coefficient is very high, in the other case the extinction coefficient is very low. So, you can immediately observe or understand that if you would shine light of wavelength 253, that would be absorbed much more by the molecule than shining light at what 375 nanometers. Okay. And that is what I meant by saying that this epsilon depends upon your lambda, it is a function of lambda. Okay. It will become more clear when I show you the absorption spectrum of tryptophan, but so just hold on. Now, if this is the case, let us calculate sigma. You know what sigma is, right? We know that sigma is 3.82 times 10 to the power minus 21, right, times epsilon. This is from 5. So, let me give you the value. So, for sigma 253, the sigma 253, if you do the math, it is about it comes to 6.1 times 10 to the power minus 16 centimeter squared. Okay. And please remember, if sigma is a cross section area, what is the unit of sigma? Centimeter squared. Volume was centimeter cube, length was centimeter, then sigma has to be centimeter squared. I should have mentioned this before, I forgot. So, centimeter squared 10 to the minus 16, right. So, I can write it as 6.1 angstrom squared, okay, 6.1 angstrom squared. So, that means the cross section area, the absorption cross section area at 253 for anthracene is given by this value 6.1 angstrom squared. Okay. Now, similarly, if you do the same thing for sigma 375, you will be ending up with the value which is 2.4 times 10 to the power minus 17 centimeter square, which is 0.24 angstrom squared. Okay. This is the cross section area at 375, absorption cross section area. Okay. Now, let us assume this. Let us assume that the molecular cross section of anthracene is 12 angstrom squared. Let us assume that the molecular cross section of anthracene is 12 angstrom squared. Okay. So, that means this is the cross section area presented by the molecule. It is not necessarily the absorption cross section area. Every molecule would come with an area, and this is the area you are talking about. Okay. Please make the difference between this and the cross section area. Okay. So, this is the area of the molecule. Now, based on this value and based on the values you just got, you think about this at sigma 253. That means for sigma, or at 253 nanometer, if you are shining this light, what was the absorption cross section area in that case? 6.1 angstrom squared. What is it for the full molecule? 12. So, what it is saying is whatever incident photons you have, because 6 is half that of 12. So, that means at least 50% of the photons would be absorbed by the molecule at any given time. Why? Because your absorption cross section area at that wavelength is just half of your total molecular cross section area. So, that means at 253 nanometer, almost 50% of incident photons get absorbed. Then you can realize that at 375 nanometers, only about 2% will get absorbed. Only about 2% will get absorbed. Okay. So, this is an example where hopefully I could convey to you the importance of cross section area. Again, I tell you, if you would suppose synthesize a dye, right? Suppose you would synthesize a dye or synthesize a compound, and you say that okay, I found this compound to absorb very strongly at a certain wavelength. When you are going to do this, the first thing someone would ask you is, what is the absorption cross section area? He would not actually ask you what is the extinction coefficient. Well, it is the same, as you just realized, they just differ by a constant, right? But what they would ask you is, what is the absorption cross section area, because that is much more fundamental. That means that is the one which goes into the equation when you derive Lambert-Beer's law. You do not start with extinction coefficient, because you do not know what it is. Okay. But just remember, what does extinction coefficient tell you? What it tells you is, if you have a high extinction coefficient, that means it will absorb strongly. If you have a, see, what was your absorbance? So, your absorbance, that means your optical density was given by this equation, right? Let me show you that. This is what it was given to you by, right? So, this is what we derived. this log of I0 by I is your optical density, essential absorbance. This is equal to epsilon C times L. C is the concentration, molar concentration, L is in centimeter. If these two are constant, that means you are taking the same concentration of any two compounds and taking the same, putting it in the same cuvette, that means having the same path length, right. Then what would the absorption depend upon? Extension coefficient. So, what extension coefficient tells you is the probability or the intrinsic probability that a molecule has towards absorbing a certain radiation. It is related to probability. Okay. Now, think about this. What is the other thing you have found which is related to probability? Here you see extension coefficient is related to the probability of absorption. What was the other thing? Remember we talked about intensity, what was that? The probability of absorption, the intensity of absorption, what was that? The Franck Condon overlap, remember? Arey? Franck ko bhul gaye? Don't forget Franck. So, anyway, that means these two have to be related. So, these two are conveying essentially similar information. Okay, try to relate these two things. We are coming from two different points, but you finally merge at the same thing because you are talking about the same transition, you are talking about the same phenomenon, right. Okay. So, this was about the derivation of Lambert-Beer's law. Please keep this concept of molecular absorption, or rather absorption cross section area in mind, because it is very important. So, let us go back and look at something a little more interesting which you actually do in practical life. Okay. If you are doing an absorption, this is a typical component of an absorption spectrometer. Okay. The typical component of the absorption spectrometer has two things, a few things. The first one is the source. Source means you have to shine light, because remember that rho nu, that energy density, you have to have that energy density. So, that energy density comes from the source, the first one, right. Then you have an entrance slit, well, do not worry about that. Then you would be having your sample which would absorb. Okay. After absorbing, it would, whatever light is absorbed, it tries to disperse. So, it would disperse using, this is a prism you see, and finally it goes to the detector where you finally get your absorption spectrum. Okay. So, these are the main components. It is simple, you have a source, you have a sample, you have a detector, and between you have some optical components. This is what you need. Okay. So, essentially what you are looking at, you are looking at the change in transmission. So, what is transmission? If absorbance is log of I0 by I, what is transmission? Log of I by I0, right. Okay. Good. So, now this is about a light source. There are in common UV visible spectrophotometers, there are two light sources you use, okay, generally. One is, it is called a UV visible spectrometer, right. So, that means you would be having a UV part, you will be having a visible part. The one which is responsible for the UV light source is a deuterium lamp. Okay. If you would ever look into an absorption spectrometer, do not be afraid, I highly encourage you to look into it. Okay. You would see these two lamps, the first lamp is a deuterium lamp. So, this is how deuterium lamp looks. So, this is typically how it would look. Now, since I have given you the picture, you can take your laptop out there, right, in front of the computer and compare it with the lamp you have inside. It should match. If it does not match, come back and let me know, okay. Then I will know something new. Anyway, on the right side is your tungsten halogen lamp. Okay. So, the deuterium lamp, look at the range of the deuterium lamp. What is the range? It is from 160 to 375 nanometers. It cannot go beyond that. That means, to go beyond 375, what you would need? You would need another source. So, for that source you use the tungsten lamp, you look at the range is from 350 to 2500 nanometers, huge range, right. Okay. So, generally when you do absorption in the UV visible, you go from say 200 to 800, okay. You do not go beyond that, because beyond that it is called near IR and you would need another detector, but it can be done. There are NIR spectrophotometers available. Okay. Now, this is typically the light coming out from a deuterium lamp. See where it peaks. So, this is 200. So, this portion is 200, okay. This is 300, and so on. You can see what is the maximum. The maximum is somewhere here, right. I think it is close to about what 250 or so, okay. And then as you see, as it goes towards 300 and down, its intensity decreases. So, this is the kind of useful range you have for the deuterium lamp. Okay. So, this is the this is the spectrum of the light that is coming out of your deuterium lamp. I would like to encourage you to look up this process. Why do you have the spectrum? What gives rise to the spectrum? Can you tell me what gives rise to the spectrum? What happens to the deuterium lamp that gives rise to the spectrum? Pi to pi star transition. Go slow, you are too fast for me. Okay. Look this up, look it up, it is interesting. Now, look at this. This is a tungsten halogen lamp spectrum. A tungsten halogen lamp spectrum, it is not only a tungsten, it is also a tungsten halogen. Okay, please keep that in mind. The halogen is present there for a certain reason. You look at the spectrum, the wavelength is in micrometers, 0.2 micrometers is 200 nanometers, right. It goes from 0.2 to 2.5, and you can see this is its spectral irradiance. That means that is what its lamp profile is, okay. And this is why you can use this for your absorption studies, right. Now, guys, you know tungsten lamp, right. Why do you need to have a tungsten halogen? Can anyone tell me?
Because there are so many photons are coming out, so we have to coat with halogens to control the number of photons coming out.
Well, you are right, but not to control the number of photons. So, you are absolutely right. What it does is, have you seen these normal filament bulbs we use, right? You would see that when they go bad, they have these black deposits on the sides, right. So, if you have these black deposits, what it means is these black deposits black, right, it would absorb some of the radiation that is coming out, and hence its intensity power decreases as a function of time. So, what does halogen do? It does not control the number of photons. What it does is it
the number.
Right, no, it not the photons. What it does is it takes the black one and brings it back over to the, that means whatever you have a tungsten deposit out there, it oxidizes tungsten and brings it back to the filament. Okay, it does not allow it to deposit out there because of a certain reaction with the halogen. That is why you need to have halogen out there. Okay, you just cannot do with the tungsten. So, if you are ever buying a spectrometer and you see it is only giving you a tungsten lamp, that is the first thing you do is do not go for that. You have to have a tungsten halogen. Otherwise, depending upon the usage, within a very short time you will see your spectrometer has gone bad. That means the visible part is not working. So, now you can realize it is a simple thing. Whenever you use it as a box, but these are the things that go inside. But see, if you are going from the UV to the visible region, right, you need both the lamps working in unison, is not it? That means they have to work together. If one of the lamps go bad, then actually you cannot do your absorption spectrum. Deuterium lamps are typically much more costly than tungsten halogen lamps, far more costly, okay. Right. As I told you, I would be showing you the absorption spectrum of these amino acids. So, look at the absorption spectrum. The blue one is that of tryptophan, right. So, this is tryptophan, this is tyrosine, and this red one is phenylalanine. Okay. Now, guys, look at this very carefully. What do you have on the x axis? X axis you have wavelength lambda. What do you have on the y axis? On the y axis you have what? You have the extinction coefficient, right. So, this is typically, if you would ever look up an absorption spectrum, this is typically how the plot would come. You see, when you get the absorption spectrum in your UV visible instrument, you do not get these things. What do you get? You get 0.1, 0.2, 0.3, whatever, right. But listen, it is very easy for you to convert it to epsilon, right. How? Because you know absorbance, that is OD is equal to epsilon CL, you know C, you know L, you know OD, you get epsilon, and essentially then you plot epsilon against lambda. What does this tell you? See, C and L are just something which you are putting in. That means you know what the concentration, you know what the length is. Epsilon is a property which is intrinsic to the molecule, as I was just discussing, because it is related to what? The cross section area. So, it is always good for you to know what the epsilon value is at any given wavelength. Now, you can see what has happened is, you look at the blue one, which is tryptophan, right. At the tryptophan, your epsilon is actually varying. Remember I said that epsilon is a function of wavelength. Now, this is what I meant. Your epsilon is not uniform throughout, okay. It is a function of wavelength. Now, here if you are looking at 240 nanometers and above, so the peak, the lambda max absorption of tryptophan maximum is about 280 nanometers. So, what does this mean? What it means is that if you are exciting at 280 nanometers, tryptophan would be having the maximum absorbance. Okay. But look at this, when you are going to excite at 280 nanometers, if your protein along with tryptophan has tyrosine, that will also absorb, because look at tyrosine. What is the lambda max of tyrosine? The lambda max of tyrosine is about, I think, 274 nanometers. Okay. But if it is at 274 nanometers, at 280 you can see it still has enough absorbance. That means, if you are exciting tryptophan and if the protein has tyrosine, the tyrosine receptors also get excited to a huge extent, just based on the absorption spectrum. Okay. Now, you come to phenylalanine. The phenylalanine we generally do not use. So, phenylalanine you can see it is about I think this is about 257 for phenylalanine. Okay. So, phenylalanine is far blue shifted. Okay. So, the two most important ones which we consider in proteins is, one is tryptophan, the other one is tyrosine. Okay. Now, suppose you would, or I would like you to selectively excite tryptophan with minimum interference from tyrosine. Where would you excite? Do not look at me, look at the spectra and tell me. You can see out here. So, this is whatever this is. So, this is 300, right. So, I think, yeah, if this is 300, so this is 300. You can see here tryptophan is still enough absorbance, right. So, generally you will see when people are doing fluorescence studies, if they are going to look at tryptophan, where the excite is, the excite at a wavelength it is known as 295 nanometers. Okay. You can see when excite at 295 nanometers, the tyrosine absorbance has already decreased to a large extent, but tryptophan is not. So, hence what you are doing is you are trying to selectively excite tryptophan, but still you have some contribution from tyrosine, but that is much less as compared to what you would have had if you would have excited at 280 nanometers. So, that is one of the reasons why when people are selectively looking at tryptophan, they try to excite at 295 nanometers. Okay. See, this is nothing new, there is not a huge thing, it is very simple. You have to look at the absorption spectrum, that is it. That is why absorption spectrum is so important for you. If you are going to do any fluorescence studies or any study, especially fluorescence, what you do is you start with the absorption spectrum, period, right. There is no alternative to that. Okay. And I will just give you the extinction coefficients. So, these are the extinction coefficients. So, look at tryptophan at 280 it is 5600, at tyrosine at 274 it is 1450, phenylalanine at 257 is 220. So, now you can understand why we do not use phenylalanine, right, because phenylalanine the absorption coefficient is very small, hence the cross section area is also very small. Tryptophan has the highest, that is why tryptophan is the one which is also most used, right. That is why we so frequently use tryptophan for our studies. Okay. So, that is what it was showed to you in the previous graph. You can see this is tryptophan, this corresponds to 5600 out here. See, this is tyrosine, this corresponds to about 1450 out here, right, and this phenylalanine, this corresponds to about 220 out here. Okay. It is just so evident from your absorption spectrum. So, guys, this is how you would read an absorption spectrum. Okay. If you are given any absorption spectrum, these are the things you are supposed to actually interpret. And remember, if you are going to look at a fluorescence, suppose you know tryptophan fluoresces, I am telling you, that is why you know, if you do not know already. So, if you are going to excite tryptophan, then you cannot excite at any arbitrary wavelength, you have to excite at that wavelength where it absorbs, because it is not, if it is not going to absorb, it would not be having any emission. So, that is why if you are going to start with a new compound which you have synthesized, again the first thing what you would do, you will take the absorption spectrum and excite within the absorption spectrum to see whether it has fluorescence or not. okay, and then other things come later. Clear? Okay. So, there is one another very important, I will just leave you at this because I have already run out of time. I will just leave you at this. I will start on this in the next class. So, if I am going to start from this, just I am going to tell you this. You look at this, ellipsoidal thing. What you have is you are zooming into a portion of your cuvette. Cuvette means your sample cuvette where you have placed your absorbing solution. Okay. Now, what are these shaded portions? So, anyway, these dotted portions are your solution. The shaded portions are what? The shaded portions are your wall, that means the thickness of your wall, cuvette wall. Your cuvette walls are not, I mean the cuvette walls have some thickness, right. So, that means the bottom line is, if you are having an incident light of intensity I coming in, there is no guarantee that the one which is hitting the solvent or the hitting the sample is actually I. Why? Because before that it has to pass through that thick wall, right, and hence some kind of absorption, some kind of scattering can happen. Okay. So, these things you have to take care of. Similarly, when you go there, when you go to I, which is getting transmitted, right, this I and this IS can be different. So, what you will see is, if you are going to do a UV visible spectroscopy, especially the UV one, you have to use a certain cuvette which does not absorb the UV radiation. That is why what cuvette do you use? You use a quartz cuvette because it has minimal absorption in that region. However, if you go to visible, you can easily use a glass cuvette because it does not absorb, but glass cuvette will tremendously absorb in the UV, that is why we will never use that. Okay. So, anyway, this is where we will start from in the next class, okay, and after that we will move on to fluorescence.